Well, good morning, and thanks for logging in, and thanks for the introduction. So, as mentioned, I'm Rich Davies, and I'm a Senior Application Engineer with EDR Modesto over here in the UK. And we're an ANSYS Gold channel partner. But notwithstanding, I'm here to help, and I like to think I'm relatively approachable, so please do get in touch if anything I present today is of interest. Now, as the presentation flyer said, I've got a long background in structural analysis using most of the common FE packages, and more recently, the ANSYS suite. But full disclosure, my experience of electromagnetic and electrochemical analysis is perhaps a bit more limited, so please bear with me. But to be honest, it does go to show that if I can undertake the range of analyses that I'm going to present today, then that's certainly no roadblock for any of you either. Now, what we're going to talk about today is how we can use ANSYS LS-DYNA to ensure battery safety in a structural sense. So if we're deforming or damaging batteries, lithium-ion cells, for example, how likely is it that they will then go on to fail, possibly catastrophically? And we're going to look at how this can be achieved through simulation and how those simulations might sit within an overall structural and safety assessment workflow. So a bit more detail about what we're going to talk about today. Now, needless to say, we've all got goals to achieve in our work. And the engineering goals we're looking at here are to ensure the structural integrity of batteries. We've all seen the effects that overcharging or mis-speccing batteries in e-bikes or e-scooters has resulted in extensive fire damage to people's homes, for example. And yes, I accept that those cells, or they may be in the cases of less than thorough manufacturers, but nevertheless, it's evident that the amount of energy stored in those cells can lead to fire, explosion, and the associated safety issues. So it really is incumbent on us to make sure that that doesn't happen in any context where we're going to deploy these batteries. Now, notwithstanding we're looking at the safety implications, but also we want to enable a means of robustly designing these batteries so they are resistant to this damage, which could then induce the problems such as thermal runaway. Well, how do we do that? This is a bit more than I've got a hammer, so everything's a nail problem. Yes, simulation really is invaluable here in ensuring this safety and by doing that efficiently. And in this context, or in this example, we can use an explicit structural solver for a drop or an impact test. But then the real beauty here, and with this environment, is that we can then seamlessly integrate that with thermal, with electromagnetic solvers, and we can quantify, for example, the Joule heating effect. And we can even then, and that will give us the capability of modeling the thermal changes, and those thermal changes will have an influence on the conductivity or the resistivity of the systems here. So all of these things will interact. We also have an electrochemical capability, and there are a variety of different battery modeling methodology within LS-DYNA, depending on what the analyst needs to or wants to achieve. And we'll go over some of those in some detail today. But what I want to emphasize on this slide really is that the power is that this is all a common FE model across all of those different solvers, and it's all driven from a single interface, which brings obvious benefits. Data transfer between those solvers is seamless. And there's an estimate actually that this can give a 3 times time saving in terms of multi-physics interactions between solvers. So if, for example, you were doing your explicit structural solve and you had to export or link that to an external solver to do, say, the thermals, and then another external solver to do the EMAG solve, that can be a bit relatively time consuming. And so there is a real benefit here and a performance benefit in having that in a single analysis environment. So not only are we enabling people's sort of means of design or robustly designing these batteries, but then we can go on and we can do things like virtual testing, which again has evident time and cost savings. Now, we're not saying that testing is going to be eliminated, especially in safety critical applications, but it may well be that you only then need to undertake a test of a final design solution, rather than incremental tests at each design stage in between. Okay, there's a cost associated with analysis. Inevitably there is, because there's time involved in doing it, but almost invariably that's cheaper than the same test that you might undertake. So analysis can be quicker and less costly than testing. But fundamentally, what we'll get at the end of the day is this imparts a real understanding, and it informs design decisions based on physics. And it enables engineers really to demonstrate compliance with safety regulation in a very timely fashion. So we can use simulation as a very powerful tool to enhance what you're probably already doing in terms of battery deployment and battery design. And this particular LS-DYNA environment within the ANSYS suite is a very, very powerful way of doing that. And I think we'll probably see some of that detail as we go on through this presentation. Now, in the title, we've said we're going to assess battery integrity with LS-DYNA. Well, actually, what is LS-DYNA? Well, it's part of the ANSYS portfolio of CAE software, and it sits primarily in the structural analysis corner. So its principal capability, and the one it's best known for, is its ability to perform explicit analysis of very highly nonlinear dynamic problems. For example, where you've got a lot of contact change or very high amounts of deformation. And you can see there in the middle, we've got a static picture of a bird impact event on the leading edge of a wing. And this is, by its very nature, a highly dynamic event. We've got a lot of contact in there. There's damage and structural damage. And in fact, the bird debris is simulated as a fluid. But this explicit analysis gives us the powerful means we can actually simulate these events. So it's originally developed at Lawrence Livermore, and then by LSTC, and then LSTC was acquired by ANSYS in about 2019. And it's now undergoing full integration within the ANSYS Workbench environment. Now, I must be honest, whilst that integration in mechanical is very good, and certainly for the structural capabilities, and it does get better with each release, for some of the more esoteric LS-DYNA options, there is still a bit of hand-holding or tweaking to the analysis deck that needs to be done in terms of model generation. And I'll touch on that later in the presentation, but I will say that the tools are there to make that remarkably easy. And then aside from the star of the show, so the structural solver, LS-DYNA includes a very, very rich multi-physics capability. And that includes, and it's not exhaustive, incompressible CFD. There's a compressible CESE CFD solver. There's a chemistry solver, and particularly relevant to us today, actually, we've got a thermal and an electromagnetic solver. It's also a very, very capable implicit solver too. So it's a very, very full-featured software suite or analysis piece of software with very powerful analysis capability. And it is complementary to the strengths of ANSYS Mechanical. But then the model on the right, really, this is just something I'm going to whet your appetite with. This is a simulation of a nail being driven into a stack of battery cells. And then what we're trying to do is simulate the temperature rise, which will follow that because we're getting shorting within those batteries between the layers. So if I just play this animation quickly, you can see here that nail is penetrating into the layers. So what we're simulating here is the structural response, so the failure of those materials. We're simulating the electromagnetic characteristics of the cells. And then when we've got a shorting condition, what we're going to get is very high current flow, which gives us Joule heating, which gives us a temperature rise. And you can see here we've plotted temperatures on the contour. So we're getting temperature of 150 degrees C plus induced by the shorting of that nail penetration. So you can see here what we've got is a means of simulating and looking at the structural integrity of our potential battery deployments. And we can ensure those meet the requirements that we need them to meet, all within a simulation environment. Then what we have here really, this is just to give you an overview of the workflow which might be involved in ensuring battery safety. So moving from left to right, we start with a means of triggering cell failure. So this might be through thermal abuse. You might have left your cell phone on the back shelf of your car in a sunny day. So you're heating up those cells. Or it might be mechanical abuse. You've dropped your phone and that cell has somehow been punctured or deformed sufficiently that will get a shorting within the cell. Now, once that cell has failed, what happens? Well, if you've got shorting, you may well then get increased current flow. Well, you will get increased current flow, and that gives you Joule heating, which gives you a temperature rise. And these can actually be pretty significant. I mean, you can lead to fairly exothermic reactions, and you'll get thermal runaway. And with that, you'll then get a swelling and a venting or swelling of the battery, and eventually some gas will be produced, and that can then lead, you've got combustible mixtures in there, so you can lead to ignition and possibly explosion. Now, I do actually know this from experience in the late 90s, where a colleague of mine was doing some testing on a drilling solution, and it required some instrumenting. And so this instrumentation and the cells were all packed into a small steel tube, and there was a short condition, and the resulting explosion did actually fire the test machine out of the pipe. Luckily, no one was damaged, but it was a very, very salient lesson in the level of energy and what can be stored in what looked like fairly innocuous little pouches, really. And then if you scale that up to the size of some of the cells we're seeing in modern assemblies, for example, electric cars or electric storage banks, then it really is obvious how incumbent it is on all of us to ensure that these things are deployed safely. And one means, or the means we're looking at today, is how we can actually simulate that and how we can include that in our workflow. There are some computational challenges to that. Let's think about some of those primarily. So, as I said, it's a relatively innocuous looking lithium-ion pouch can be subject to a range of very complex multi-physics. We've got to account for the mechanical behavior. The different materials within the cell will all have different varying mechanical properties, modulus, strength, plasticity, or crush behavior. We also need to account for the electromagnetics, so Joule heating, how the current will flow, the resistance to that flow. And then we've got electrochemistry to contend with. How is the charge stored? And what level of charge is available within that cell? And then we get onto thermals. As that current flows, the resistance will inevitably lead to a temperature change, which then has a knock-on effect on the resistivity or the conductivity of the materials involved, or even on their modulus. So all of these things need to be coupled. I mean, it's fairly evident that there's a wide range of interaction physics here. Now, that really is music to the ears. We've got someone who's music to the ears of someone who's got LS-DYNA available, because we have all of those multi-physics capabilities built in, so we can simulate them. We also have a very wide range of length scales to be considered, which really does initially gives the analyst some food for thought. We don't want to discretely model everything, because you're looking at length scales from, say, a meter long for the battery size in an automotive application, right down to fractions of a millimeter for a cell layer thickness. And if you modeled all of this detail explicitly, you would end up with models with more degrees of freedom probably than you've got atoms in the known universe. So we must be careful how we model these. And the devil is always in the detail. It's at the smallest of scales where the shorts will trigger the thermal runaway. But then we have to basically contend with that level of analysis, but also include that in an overall structural analysis or a model of the whole battery. So we need some means of doing this efficiently. And luckily, we've got those means within LS-DYNA. We also have a wide range of timescales to contend with. Crash events or drop tests will give a response in the order of milliseconds. But then we also need to consider thermal problems. And especially in batteries like this, you can have these can be sort of in terms of hours or even days. So we've got a wide range of length scales and also time scales to consider. Now, I will tell you why there's a forward focus shown on this slide, and we'll go on to why that is in the next slide. So really, I'd like to give you a bit of background on where this capability within LS-DYNA originated. So it was born from a requirement at Ford, where they had a need to assess the safety of batteries within an automotive context, naturally, with a view to ensuring safety on crash. So you can see here they published a number of papers on this integration, and they really are worth a read if you're involved in this field. And it was a project undertaken in collaboration with LSTC, so the LS-DYNA developers at the time. But, and I must emphasize this, note that red asterisk, this is not solely limited to automotive. And the methodologies that they've developed are generally applicable where you've got battery technology being used. Now the code is now integrated in LS-DYNA, and it's been part of that suite since release 10. So it's relatively mature, and I will say that with each release, more and more functionality is being included. It's a real focus at the moment. As you can imagine, with the current drive towards energy storage and ecologically sound motoring and electric motors, then there's a real strong interest in this functionality. So this gives a bit of background. And then let's go back. So we'll consider what we're going to cover today. Now, for the sake of limiting this presentation, we will probably cover, or we will cover the discussion, we'll cover the steps contained within that red box. So we're going to look at the thermal and the structural abuse, and then the associated dual heating and thermal runaway conditions. But I will say that the gas release and the swelling can be simulated, and the eventual combustion as well. But I'm not going to cover that in today's webinar, but please bear in mind that additional capability is there. How is it achieved? Well, I'm running the risk here of losing some of the audience by putting equations on the screen, but I really don't think it should. What we're showing here is the interaction between the different solvers and the data and information which they interchange. For example, you can see that the displacement and the temperature interchange between the mechanical and the thermal solvers. Now, in essence, at a particular dynamic time step, the thermal solve will be done and the updated temperatures will be fed back to the mechanical solve and vice versa. And similarly, you can see that the thermal solve interacts with the electrical and the electrochemical solvers, so we can get a prediction of the dual heating. And if you think about that, if we heat up a material, its conductivity and its resistivity will change. And then using these coupled analyses, we can account for that within a single analysis environment. Now you also see there's an ICFD solver there, so an incompressible CFD solver. In fact, there is a compressible CESE CFD solver as well available. So we can even really go to town. We can model cooling and fluids within these systems, but I'm not covering that today, chiefly because my experience of CFDs is more limited. So in terms of how these batteries are actually modelled, well, it's achieved through the use of what are called equivalent circuits. So within each layer, or within each cell, the layers of that cell are discretely represented. So the collectors, the anode, the cathode, and the separator. And you can see a graphical idea of that representation down the bottom here. And then what we do, we represent those layers, and then we put between them the distribution of what are called equivalent Randall circuits added. So you can see this Randall circuit here. And this is a combination of resistance, capacitance, and this enables us to then simulate the electrical behavior. Now, I did say that all of these layers are discretely represented. Luckily for the analyst, this is done easily within the model definition, and we'll see that later on. But in essence, what you can see is the Randall surface or the Randall circuits are imposed between matching nodes or matching surfaces for shell elements. And then the layers between them are derived from the applied properties that we've got in there. Now, this is a mathematically very efficient way of doing this, but it maintains accuracy. So the parameters and the characteristics that we put into the model are defined or derived from test or available data. And it may well be that if you're deploying these systems in the field already, you have those data available. So you may well have the material properties and the characteristics of the cells to hand. Now, one of the real strengths of this approach is it gives us the capability to model internal shorts. You can see down here that when these layers are compressed together sufficiently, what you can get is a short condition between the two conductors on the outside. And you penetrate it through the separator, so the anode or the cathode have collapsed. And this short condition, we can then simulate by removing the resistance. So we can just have a very straightforward means by which that current can then flow through that short condition. So what's happened is a structural response has initiated that shorting, and then we're looking at the thermal and the electrical behavior that's induced by that. Now, I must highlight this battery modelling capability is seeing one of the real strengths at the moment of LS-DYNA, and the current market conditions are such that there really is a lot of effort going into developing further capabilities for this. So I think with each release, in the next few releases, you're going to see a lot more power in this software capable or this simulation capability, but nevertheless, there's a huge amount of power there available already to simulate what we need to do. Well, I think I'll give you a brief respite from static slides. What we've got here is a simple example. In fact, it's one of the ANSYS tutorial examples, and it's of a steel sphere impacting a stack of 8 cells. So you can see that each of the cells is represented with finite elements. In this case, we've got thin solids. So this is an 8-noded solid element, but with a shell formulation, which means it's a very computationally efficient means of modeling this system. And then within each of these cells, or each of these elements, what we've done, we've got representation of the anode, the cathode, the separator, and the collectors, and stacks of those. And you can also see the cell terminals on the left-hand edge. But whilst within each element there are many layers, we don't have to have a single element for each layer. And this harks back to that length scales point I made earlier on. There are some modelling abstractions available to us where we can reduce the detail in this model whilst retaining the physics, or the detail in the physics that we need to represent. But let's have a look. So if we animate this, you can see here what's happening is that steel sphere is coming down, it's impacting on the cell, and we're getting significant deformation. And what you're going to get is sort of sandwiching up of the cell layers in between. But it's not necessarily obvious from the structural response how this might affect the thermal response. So then what we'll do, we'll look at a cross-section of this, and we're going to plot the temperature change as that impact progresses. And you can see here, as you can imagine, red indicates a higher temperature. So as these layers are crushed by the impact, what we're doing, we're inducing that shorting. That leads to increased local current flow, which gives us Joule heating and the temperature rise. And this is all done within a single simulation environment on a single FE model. So really quite a powerful system, I think. So we can see there we've got the structural response, which then leads on to that thermal response. Well, I just want to add some meat to the bones of the description of this model, really. There is a lot more detail in the references shown there. And I strongly recommend that if you're in this field, you read through some of these references. The ls-ansyscom.com link is particularly good. And what we've got here is a graphical representation. So you'll remember we saw that fairly simple model. And this is a graphical representation of how the layers are represented within each of those elements. So we don't have an individual element in the structural model for each of these different layers. So this is it's just giving you an idea of where you've got cathode, anode, separator, collector. When I say that they're not discretely there as individual, actually what happens in the thermal and the electromagnetic soils, they're automatically recreated as thin elements, solid elements for the analysis, but that's done efficiently, and that's not for the analyst to do. The analyst just has to generate a mesh that looks like this. And I would really recommend that you read these, if you're in this field, have a read through these. They're very digestible, easy to read, and a good source of information, far more comprehensive than I can cover today. Now, to give you some idea or understanding of how the electrochemical behavior is characterized, as I've said, we've got an equivalent distributed circuit representation. But we do need to derive the properties that we're going to put into each of these cells from test, unless those data are available. So we're going to need a capacity test, for example, to assess the level of charge which can be stored. Similarly, we need some idea of how rapidly these things can discharge. So we need a slow and a rapid discharge test. And from those, we can derive the character or the properties, the parameters that we'll put into our Randall circuit. And then once these data are available or derived, it's always worth a quick validation simulation, I think, to verify that our model is capturing the test. And if these models can be rolled out and deployed generally. And you can see this is a fairly standard approach, isn't it, where you do test and then test validation. And we can see here that we're getting very close correlation between test and experiment. So this gives us confidence that we can then roll out these simulation methods to battery technology we might be deploying in the field. There's a mechanical analog to that. So in a similar manner to that electrochemical testing, we're going to need some mechanical testing to give insight and data for validating the structural predictions. So the mechanical properties of the cell assembly, for example, the modulus or the crush behavior of the anodes and the cathodes, are all going to be represented. And so these data need to be input as characteristics. That's very likely that you've got materials data available, or if you haven't, there is the ANSYS Granta database, or they might be derived in-house, or you might be provided them by the cell manufacturer. But these are then input as characteristics into the model, and we can do our validation analyses, and you can see here we're getting very good correlation on the force displacement response of various different indenters on the cell structure itself. And similarly, you might do a thermal test where you're actually monitoring the voltage and the temperature as you're inducing this mechanical shorting, and then you're going to be able to validate that we can simulate these smaller sort of unit cell characteristics or behaviors before we deploy that in a larger scale model. But all of these data clearly were used originally when they were implementing this solution. And so there is great confidence already, but it's just a nice sort of visualization of how you might achieve further validation within your environments. Just another example, really. This is a simulation of the using what's called actually this is the crushable foam model. So LS-DYNA has got a wide variety of material models available within it, and the crushable foam model was used in this instance to simulate the mechanical properties of the anode and the cathode. So you can have a variety of different indenters, and again that force displacement was measured on test and then predicted, and good correlation was shown. And it's certainly in terms of the structural response, I mean, this is very well established technology. I first used the foam material in 2001, I think, in an aerospace application. So there's great confidence that all of these methods work very well. And then the other piece of the jigsaw, well, that's the thermal validation. And again, you might achieve this through comparison with test. It's worth pointing out that these analyses have been done in the original development of these methodologies, so you don't have to do this necessarily in-house. There is a learning benefit to doing some of these smaller scale analyses, but the very fact that they've been integrated, Ford and LSTC developed and underwent a lot of testing of these methodologies so that there's good confidence in their accuracy. But nevertheless, it may well be incumbent on you, depending on the regulations that you've got to satisfy, that you need to do some more local testing before you then deploy larger scale batteries in practice. But one key thing I'd like to show here, actually, this is a thermal runaway condition. So you can see, for example, I mentioned earlier, we were looking at the timescales. Well, this is actually 200 seconds, relatively stable. Before we get in this internal shorting, it then suddenly leads to a thermal runaway. So this gives you an idea that, yes, we do have to consider not only a large number of length scales, but also time scales in our simulations. And this can all be accounted for within this LS-DYNA environment. And then once we're happy with these sort of unit cell examples, then we will integrate that in the full scale analysis. Now, rather shamelessly, yes, these are automotive examples, but I think the complexity represented here makes it clear that it's more than likely equally applicable within your assemblies. So we've got drop tests here, we've got penetration tests, and all of the associated multi-physics solves are very achievable within a single simulation environment. Now, in these instances, I suspect the workflow would likely involve model generation within ANSYS Workbench. Certainly, if you're doing complicated meshing and mesh generation, then that is a very comfortable environment to do that in. And then you can either use what's called keyword snippets, and I'll show a brief example of that in a moment, to represent the detailed electromagnetic characteristics, for example, within the model. Or you might do some of the pre and post processing in LS pre-post, which is another piece of software, a pre and post processor software that comes with LS-DYNA. And I'll give you a glimpse of that in a moment. But I think these models here, the complexity of these models, really gives you an idea that this technology could be equally applied in whatever field you need it to be applied. Again, enough of static slides. We've got the same basic model here as we had earlier, but in this case, what we've got a steel conductor that we're going to pass over the electrodes at the end of the cells. And then what that's going to do, that's going to short those cells. And it's going to be interesting to see how the temperature changes as that occurs. So maybe not the most compelling animation at first, We just got a steel plate passing over those conductors. But then when we show the temperature, this really brings home the sort of value of these analyses. So you can see is that shorting condition is brought across those conductors. We get an increase in the temperature of the cell. And it's worth noting that can actually build from the reverse end of the cell. So not always intuitive, as you might expect. So if we do this side by side, you can see that temperature rising. You can see how that then propagates through the cell. Now, this can obviously be done in much, much more complicated assemblies, but the same principle applies. So now, at the risk of doing live demos, I'll just give you a very, very brief insight or indication of how we might generate these models. So first of all, what we might do some meshing in ANSYS Mechanical. ANSYS Mechanical really does have a very good integration of LS-DYNA. To be honest, that has been primarily focused on getting the structural side of things working at first, but there is more and more integration coming. And you can see we've got SPH capabilities or coupling capabilities. We can do a wide variety of things. We can do airbag modeling, perhaps less relevant to your industry. But this is where we would do our model generation. Now, if you're familiar already with the mechanical environment, then it's not a great step to then start doing LS-DYNA. But I did mention, so we'd do our geometry definition, we would generate a mesh in here, and do all the boundary conditions as we would in the mechanical analysis. But then when we got these more esoteric sort of electromagnetic characteristics that we need to define, we can then do things so we can insert what's called a command object. There we go, commands. And what this enables us to do is have a direct text input to the input deck, so that the underlying piece of data that LS-DYNA then uses to generate these solves. And so we can input here our electromagnetic capabilities or characteristics. Now, that's a really neat way of doing it, and then you have a self-contained mechanical or workbench file to do it. There's an alternative, or there's a complementary means of doing it, and that's using what's called LS Pre-Post. So we can export our model from mechanical, we can bring it into LS Pre-Post, and really this has a very, very strong coupling with LS-DYNA. So we can then go in and we can see in here, for example, we can look at the EM section of the model. So this is the electromagnetic section of the model. And you can see we've got various entries here for defining some of the behaviors. So we're defining some of our Randall circuits, for example, here. Let's click on one of these. So we can see we're setting up a Randall's short. And then if we look at the Randall's T-shell, so we can see now here, this is where we're starting to put in like data such as cell capacity or conversion factors. So this is where we put in our parameters that define the behaviors of our Randall cells. And it's a very, very closely coupled link between this and the eventual solve. So whilst mechanical, you can do pretty much all of the structural model definition you need to do, there may be instances where it might be more straightforward for you to bring that element or bring that mesh into LS Pre-Post and do some of the model definition in here. But what I would like to show you is, so we've got not only the electromagnetic, we've got structural in here, so we've got crushable foam represented. So we've got the densities and the moduli you would expect. But then down here, this is where the real detail is. So you can see we've got a composite T-shell. And don't worry about the details necessarily, but what that is, that's a thick shell composite. So we've got a layered definition within each of these elements that you can see here defined in some detail. We've got various layers are introduced into that structure. And we've got, say, the conductor, we've got the anode, the separator, the cathode, and then another conductor. And we can build up quite a rich section of behaviors across the depth of that cell. So within that individual element, we've got all of these different layers that not only structurally represent the behavior, but also thermally and electrochemically. And it's a neat way and a very easy way of then just going in and checking the model to make sure that you defined what you need to define. And then we can put in, for example, here we've got an initial velocity on that rigid body here, on that steel body. We can define temperatures. So this is where a lot of the model definition is set up. It may look a bit less friendly than the very attractive GUI of mechanical, and I would imagine that as the releases go on, then more and more of the electromagnetic or EM capability can be introduced or will be introduced in mechanical. And it can be done. We can do all of this using keyword snippets, but it really is straightforward. And what I'd like to just absolutely emphasize, one FE model for all of these different solves: the thermal, the electrical, the structural, the electrochemical. So it's a really, really powerful system on what looks like a very, very simple model. But I think you've probably heard enough from me. It really was just a very scratch the surface introduction. But I'd just like to summarize. I think what we've shown here, or what I've shown here, is that we've satisfied the goals we wanted to demonstrate. The solution really is seamless. We can integrate all of these physics within a single simulation environment. And that ease of integration has both cost and time-saving implications, and it also makes the analyst's life so much easier. Now, there are many different battery models available. I've only scratched the surface here, and they all have different applicabilities depending on the level of accuracy or model detail required. There are some meshless methods available, for example, which are very, very efficient at solving, but may not give you some of the detail you need. Again, let's just focus on that. This is all within a single FE model across all physics. And I really do think that the benefits of that speak for themselves. Ultimately what we've got here is a means of being more informed about our design decisions and how they might affect the structural integrity or safety of batteries. And certainly for batteries that we might be deploying in the field in safety critical areas, it's incumbent on us to make sure that they will behave as we expect. So really, I thank you very much for your time and your patience in listening to this. And I do hope it's been of some interest and relevance, and that it's piqued some enthusiasm for you in starting to look at simulation of these systems. And I believe now we're available for a bit of Q&A. But what I would say is please don't hesitate to get in touch if you need any more detailed information, or if there's something I've missed here that you've got a burning desire to have more information about. Thank you very much.
So we've had a couple of questions come through. So first of all, is there a physics-based electrochemical model in LS-DYNA? Yes, there is. So you can see down on the right-hand side of that slide that's showing on the screen at the moment, it's actually that electrochemical model of the battery system. And so is where you would put in your characteristics of the electrochemical side of the battery physics. Now, if you want some details of that, I'd be more than happy to drop in an email, or we can have a follow-on call from this. But it's a fairly rich and fairly powerful functionality, to be honest, and we can represent a lot of the electrochemical characteristics of the cells. Now that does then lead on to the second question that was being sent, and is there a means of modelling sort of cell aging or degradation over periods of time? Now, not necessarily a way of simulating how the sort of the chemical or the electrochemical behaviors will degrade over time, but what we can do, we can put in sort of time-dependent things like charge carrying capacity. So if you have test data of single cells or cells that we can then derive an aging characteristic from, then they can certainly be input into the model as a time dependency. So yes, we can certainly simulate the chemical behavior of these cells. And then we can also simulate the sort of degradation, but the degradation would require a certain amount of test data being available. But those data are available, they're readily available. Almost invariably, if you're in this field, you will have either used some sort of level of testing, or there will be data available to then input into these models. So what this means is that we can then do accelerated simulations of the more specific or varied cell configurations that you might have based on test data. So it really is it's a very powerful means of simulating battery behavior, both physical, electrochemical, and thermal, You can see here we've got the multi-physics capabilities. So what I would say is that if you do have any questions, or if this presentation has piqued your interest at all in going further with doing some of these simulations, then please don't hesitate to be in touch with us. We like to think we're very responsive at EDR, and we do get involved, and we support a lot of people who are doing this sort of analysis. So if this has piqued your interest, if you've got further questions or comments, then please don't hesitate to get in touch. I know that I'm very aware that everybody's time is their most valuable asset. So I'm very, very grateful that a number of you have managed to stay on to the end of this webinar and been patient enough to listen to me talking about this. It's almost impossible to cover in 43 minutes the level of detail that we can simulate in this environment. But it does it's given you a brief taster into how it works, into how that simulation can be undertaken. So I would implore you that please be in touch. If this has been of interest, if you've got further questions or comments or any information that you need, then please don't hesitate to drop us a line, and we'll endeavour to get back to you as quickly as we can. But I think that's the only two questions that have come out of this live. So perhaps I'll wrap up there. I will, as I say, very grateful for your attention, very grateful for your patience, and thank you very much for attending.
We do actually have two more questions that have come through since that started. So the first one is, are same electrical chemical model parameters used for all elements of one cell?
Yes, they would be, although you can define different regions. So you could obviously have separate regions within the model with different characteristics. So you can have multiple cell characteristics within a single simulation environment.
Great. And the other one was, when you say meshless model, what does it mean?
Well, there are two ways of doing this. So the meshless model, that is exactly as it says. So some of the characteristics don't necessarily require an underlying finite element mesh. So fundamentally, and I'm a structural engineer by heart. So my entire life has been in generating finite element meshes. My career. So the nodes and the elements. But there are meshless, so there are means of then sort of simulating the Randall circuits that don't require that node and element. So it's a simplified means of doing or deriving the right characteristics and behaviors within the model that can then be mapped back onto that finite element mesh for the structural response.